Right, so we now start solving the exercises of this section. So in this first one, we have to use the proposition 731, the first proposition, to prove corollary 732. So let us first recall the corollary. Proposition 731 is the condition that tells us precisely when a series of non-negative real numbers is convergent, namely when its partial sums are bounded above by some positive real number. So that's what proposition 731 states. And let's see the statement of corollary 732. It has a name also, if you recall. It's called the comparison test for infinite series, and we are just going to recall what it states. I mean, the gist of the statement. We are not going to write the entire statement, of course. So here we have two formal series of real numbers. One is summation an and the other is summation bn, where n is some integer, such that these inequalities are true. The absolute value of an is less than or equal to bn for all n greater than or equal to m. These things are given. Then if the second series is convergent, let me just write like this, is convergent, then that implies the first one is absolutely convergent. That means this series is convergent. This series is convergent. When that happens, we say that this is absolutely convergent. That is the definition of absolute convergence. And when these things are true, this sum is less than or equal to the sum of the second series, and this of course is greater than or equal to the absolute value of the sum of this original first series. We have to prove these things now. Okay, so that means what we are given is that this second series is convergent. So we start off with its convergence. Since summation bn is a convergent series of non-negative real numbers. And where is this non-negativity coming from? It's coming from these inequalities themselves. That is because we already know that the absolute value of any real number is greater than or equal to 0. So because of these inequalities, all the bn's are non-negative. Okay, so that's how we get not just a convergent series but a convergent series of non-negative real numbers. So that is why so that means to this series we can apply proposition 731 by proposition 731, there exists a real number M such that all these partial sums of the second series are less than or equal to M for all integers n greater than or equal to small m. Okay, so now from the given hypothesis that the absolute value of a n is less than or equal to b n, and the comparison test for finite series, we are going to recall these things. We are going to refer to the actual results, which is going to be what? Lemma 714f. Part f of lemma 714 has the properties of finite series. Among them, part f is the comparison principle for, the comparison test for finite series. So we are now going to use that. So by the hypothesis, just for the sake of understanding, let's also mention what hypothesis precisely. That an has absolute value less than or equal to Pn for all n greater than or equal to m, and lemma 714 part f, we have for all n greater than or equal to m. To put it more simply, we have just added all these inequalities. Less than or equal to bm plus 1, and the last one is this. If we do that, then we get this first inequality, and the second one of course is coming from this. So what does this tell us? This tells us that the partial sums of the series summation mod an are also bounded above by some positive real number. That is why, again by proposition 731, this series, which is of course this is a finite series, but if you had an infinity here, that series is convergent. That means the ordinary series summation an is absolutely convergent. Hence, by lemma 731 because the first one of this section. Again, this series is convergent, implying that our original first series is absolutely convergent. And then we are not done yet because we have to prove those final inequalities also, and they will now follow from this thing. Okay, this is of course not a single inequality. We actually have infinitely many inequalities here as you change n. Now from the last inequalities above, that means this, and you can probably guess what we are going to do. We are going to take limits on both sides as capital N approaches infinity. But in order to be able to do that, we need a result, right? And that result is going to be lemma 6 for 13, which in fact has the name comparison principle. If you recall, there was a comparison principle that we encountered in the chapter on limits of sequences, that is sequences of real numbers. So from the last inequalities above, let us write within brackets by lemma 6 for 13 we have these things: summation this infinite series sum is by definition the limit of this sequence of finite series sums as n approaches infinity. This thing will be less than or equal to the limit of summation bn as n varies from m to capital N, and that is equal to the sum of the second series. So we have obtained one of the inequalities, and in obtaining this inequality, this is where we are precisely needing lemma 6 for 13, the comparison principle. And the other inequality is actually we already had this. So let's just adjoin that with this one. The inequality is part of a previous result, and that is proposition 7 to 9. So this completes the solution and the proof of our corollary. Next, proof lemma 733. And hint is given, elaborate hint. For the first part, recall that lemma 733 is the result which gives us the precise condition when a geometric series is convergent. And when it is convergent, it also gives us the formula for the sum. So it's that thing. So in that there are two parts, of course. In the statement there are two parts. For the first part, use the zero test. We are, of course, before writing the solution, we are going to recall the statement of lemma 733. Then it will become clear what the first part is and what the second one is. Use the zero test. For the second part, first use induction to establish the geometric series formula. Ink is needed. Geometric series formula, this one, summation x to the power n, where n now varies from 0 to n, that is equal to 1 minus x to the power n plus 1. Do you recall that in school, when we encounter geometric series for the first time, we memorize this formula? So it's coming from there itself. and then apply lemma 652. Now before we do these things, let me just make one remark at this stage. You may see that Professor Tau has actually given away almost the entirety of the solution. That is the strategy for how you should proceed. And it is almost always the case that this is the most difficult part of a solution. That is to know what the steps are that you have to take. Of course, the individual steps, I am not talking about this particular hint, okay, I am talking about in general, a general problem. You have a mathematical problem, you have to first of all roughly figure out how to proceed, and then that itself will have some steps. Then you carry out each step, all the steps you take successfully, and you reach the finish line, and the solution is over. So what I am trying to say here is that figuring out which steps to take is much more difficult than proving the individual steps. That is, most often that is the case. So that is why here in fact everything has already been given away. You just have to do these things, and it's almost mechanical because each step is not that difficult. None of the steps is difficult. Okay, so let us now first of all recall lemma 733. And that formulating the strategy of a solution is in fact more than half the battle. So what this states is this: x is a real number, and we have this formal infinite series, which we know as the geometric series. Sometimes we call this x the common ratio. Now the lemma states that if the absolute value of x is greater than or equal to 1, then the series is divergent. That is the first part. And the second part is this: if the absolute value of x is strictly less than 1, then our series is convergent, and in this case the sum is 1 over 1 minus x. That is the statement. So we now have to prove this. So okay, I wrap this up now, this part. In this part the hint asks us to what it tells us to do is that we have to use the zero test. The zero test for convergence of an infinite series is a necessary condition for convergence. That is, if you are given an infinite series of real numbers which you know is convergent, that is, this is convergent, then that implies that this limit exists and is equal to 0. So that means this condition is necessary for convergence. If you have convergence, then this is necessarily true, but the condition is not sufficient. We already we have seen this. The harmonic series forms the counterexample to the reverse implication, which is not true. Okay, so to prove divergence, this is often very useful, and in this case precisely that's what we are going to use. So let us start the solution. If the absolute value of x is greater than or equal to 1, then the limit of x to the power n either does not exist or is equal to 1. But that itself comes from a result on limits which we have to mention. Then by lemma 652, the limit either does not exist, and that is precisely the case when the absolute value of x is strictly greater than 1. Or exists and is equal to 1, and this one happens when absolute value of x is equal to 1. That is not entirely true. The thing is that if absolute value of x is strictly greater than 1, then this limit does not exist. That is true. But when absolute value of x is equal to 1, then there are two cases. Either x is 1 or minus 1. When x is minus 1, then the sequence x to the power n is the alternating sequence minus 1 plus 1 minus 1 plus 1. So that is divergent. In that case, you get a divergent sequence. But precisely when x is equal to 1, you get the constant sequence 1 1 1, which converges to 1. So our statement is true, but what I said just now is not entirely true. This is the precise situation. But in any case, if these inequalities are true, this inequality is true, then this limit either does not exist or is equal to 1. That means it is never equal to 0. So by the zero test, our series has to be divergent. So let's just simply write the zero test. No need to mention the number and such things. And anyway, you can mention the number only within this text, this book. Outside of this book, lemma, for example, lemma 652 does not have any meaning. So by the zero test, this is divergent. Then we go to the next case. Next, let the absolute value of x be less than 1. So again we proceed just like what is given in the hint. We now prove by induction on n, which is a natural number, that summation of x to the power n as n varies from 0 to n is equal to The induction is extremely straightforward, but just for the sake of completeness, I am going to prove it here. This is equal to 1 minus x to the power n plus 1 divided by 1 minus x for all n belonging to the set of natural numbers. Do you notice one thing here in this claim that we are now going to prove by induction? You have 1 minus x in the denominator. Can it ever become 0? If that possibility is there, that means we are stating something that is not entirely correct. Luckily, that possibility is not there. And when will that happen? Precisely when x is 1. But x cannot be equal to 1, because if x is 1, then its absolute value is 1, and 1 is not strictly less than 1. So this condition saves us from that pathological case. Okay, so let us start the induction. Note that, so the base case will be when capital N is 0. This is equal to x to the power 0, which is equal to 1. And 1 is equal to 1 minus x divided by 1 minus x. And the numerator can be written like this: 0 plus 1 divided by 1 minus x. Again, we are able to write 1 as 1 minus x over 1 minus x because 1 minus x is non-zero. And there is one more thing here that let me just tell you about that. You see that although x cannot be equal to 1, but it is possible that you have x equal to 0. That is covered in this case. Now, if x is 0, you get 0 to the power 0. So, am I writing 0 to the power 0 equal to 1? Yes. That case is also included in this statement. Now, in some analysis books, texts, 0 to the power 0 is considered as an indeterminate form, one which has not been defined. But in this case, I mean in this text, the author has decided to define it to be equal to 1. The thing is that if one defines it to be equal to 1, no problem occurs. Okay, so there is no logical contradiction in writing 1 in place of 0 to the power 0. But of course, that is not that is not something that was decided whimsically, like someone decided to just simply write, okay, 0 to the power 0 equal to 1. It has been found that no problem occurs if this additional definition is introduced. Okay, so there is actually no problem. If you don't define and treat 0 to the power 0 as an indeterminate form in the sense that it has not been defined, that is also okay. But if you do that, then you have to actively avoid having this case. And in that case, you have to modify this by mentioning that, okay, x is not equal to 0. Okay, let me just also tell you quickly, what would one do if this definition is not considered? If for them 0 to the power 0 actually is undefined, it's an indeterminate form. How would one then handle everything here? Very easy. You see, what do we have to prove in this case? Namely, that the original infinite series is convergent. If x is 0, what is the series? The series is just the series where all the terms are 0. And of course, looking at the partial sums, you just see that the sequence of partial sums is also the constant sequence 0, which converges to 0, and that's it. So you just simply get the fact that the series is convergent, and the formula that is given, that the sum is 1 over 1 minus x. Oh, but in this case, okay, what? No, okay. No, what I said is not entirely true. You have to modify other things also, because this possibility is still there, no, n equal to 0. So if I don't have 0 to the power 0 and I am still putting n equal to 0, then it will be a little problematic. So you have to take n equal to 1. But you will see that if you just simply proceed by considering that case separately, you will still get the thing, I mean, whatever you are trying to achieve in this case also will be true. I am not going to dwell any more on this. Just wanted to tell you that some of you who may feel that we are making a mistake here, this is not a mistake. You can see for yourself what happens in that case if you don't have 0 to the power 0. Anyway, we have our basis for the induction. That is the claim is true when n is 0. Now next, let the claim be true for some arbitrary but fixed n. This is not infinity, this is n 1 minus x to the power n plus 1 divided by 1 minus x for some arbitrarily fixed natural number capital N. When I was going through this text for the first time, at one stage I also thought that professor made a mistake by writing 0 to the power 0 equal to 1. But then I searched on the net and I got to know that this is not a mistake, it's a definition that can be made if one wants. It's like the empty set. You can in fact deal with sets without ever defining the empty set, but you have to then actively avoid those cases where a set may be empty. It's a situation just like that. Then summation x to the power n varies from 0 to n plus 1, that is equal to, using the basic properties of finite series, plus x to the power n plus 1. And in place of this we can put this expression, our induction hypothesis. So after simplifying things, x to the power n plus 1 times 1 is n plus 1 minus x to the power n plus 2. So these two terms cancel out and we are left with this. And this is actually what we expect. And so this completes and proves the claim. Now we again know from our result on sequences of real numbers and their convergence that when the absolute value of x is strictly less than 1, this sequence converges to 0 as n approaches infinity. So that we are now going to use, because we have the partial sums for the geometric series and they look like this, and the partial sums have the terms of that sequence. But what is the, again by that same lemma. Now by lemma 652, limit of x to the power n as n approaches infinity is equal to 0. Therefore, the sum of the geometric series, which by definition is this, the limit of the partial sums, that is equal to and using the usual limit laws for sequences, that equals this, which is equal to 1 over 1 minus x. Okay, so this is you can view it like this. Etc. when the absolute value of x is less than 1. We sometimes confuse ourselves in thinking that this is binomial. This is coming from the binomial theorem because it looks like a binomial expansion, simply because there are two terms. But that's not actually the case, because one of my friends just a few days back said that he was thinking it comes from the binomial theorem, but then I told him that that is not the case. It's a small confusion, but nevertheless sometimes we get confused. Anyway, so that completes the solution and also the proof of our lemma. Next, there is only one more exercise, so let's just finish it. Let summation an, in this case let me just say a few more words about this series having this sum. Right now we are starting with a series and we are getting a real number as the sum. In this particular case, you may notice that actually that whatever sum we are getting is not just simply a fixed real number but is a function. Later on, when we study expressions of functions as infinite series, particularly those things called analytic functions, there we will see things like Taylor series, Maclaurin series. There we will go in the other direction. We will be given some function and we will see whether we can express that function as an infinite series which looks like this. This kind of series which have powers of x or powers of x minus a, where x is the independent variable of the given function, are called power series, and they have a very beautiful theory. In fact, when we get to power series, we will truly know what these elementary functions are: exponential function, logarithmic function, trigonometric function. From their power series definitions, in fact that's how they can be defined, we will be able to prove that they are continuous, differentiable, integrable, all those things will come. Okay, so 7, 3, let this be an absolutely convergent series of real numbers. And the magic of analysis cannot be actually fully appreciated by just working with real numbers unless we expand our view and see everything in terms of complex numbers. We won't really know what is happening. We are only looking at a restricted view of what is out there. Absolutely convergent series of real numbers such that the sum of the absolute series, if I call it that, is equal to 0. Show that all the terms of the series themselves are 0 for all natural numbers n. So it's given that this series has sum 0. Let Sn be defined to be the nth partial sum of this absolute series for all n greater than or equal to 0, that is for all natural numbers capital N. Then by which one should I mention here? Lemma 731, or actually going back to the source of all these things? I think I have to mention that both the things. Okay, then by lemma 731 and sorry, it's not lemma, this is proposition, the other one is lemma. and lemma 638 0 is less than or equal to Sn, which is less than or equal to 0 for all natural numbers. And so let me here explain what is happening. You see, this is a series of non-negative real numbers, because all the absolute values of n are by the nature of absolute values non-negative, and they are real numbers. So that means this is a series on which proposition 731 is applicable. That is, this series is convergent if and only if the partial sums are bounded from above by some positive real number. Okay, but even going further back than this criterion for convergence of series of non-negative real numbers, which is there in proposition 731, and in fact the reason why proposition 731 is true, for that we need to go back to lemma 638, which tells us what? It gives us the criterion for convergence of a monotone increasing sequence of real numbers. Recall that you have a sequence of real numbers there. We have an here now, so let us take bn. Say bn is a sequence of real numbers. Bn is said to be monotone increasing if you have these inequalities and so on. Okay. Now this type of sequences are convergent precisely when all the terms are bounded from above by some positive real number, and when that happens we can in fact say precisely what the limit will be. If you recall, the limit of this sequence is the supremum of all the bn's. This is where proposition 731 is coming from. Now, in proposition 731, we have what? Some series of non-negative real numbers, and the sequence that on which we will apply this result of lemma 638, that sequence is simply the sequence of partial sums, this one. This sequence is monotone increasing because all the terms are non-negative, that's why. So this sequence is like the sequence bn, and convergence of this sequence is just the convergence of the series by definition, and the sum of the series is just the limit of this sequence. So that means what is happening here is that the sum of this series, that is in our particular case this series, is just the limit of this sequence, and that limit is given to be equal to 0, and that limit by this result lemma 638 is the supremum or least upper bound of the set of all the Sn's, and that is why all the Sn's are less than or equal to 0. This limit, by the nature of all these things, is actually the supremum of the set of all Sn. Being supremum, it's after all an upper bound, so all the Sn's are less than or equal to 0. And because we are dealing with a series of non-negative real numbers, so all the partial sums automatically are also non-negative, so that is why they are simultaneously greater than or equal to 0. So now they will become equal to 0. That is the reason for having these inequalities. Thus Sn is equal to 0 for all n belonging to n. From this, one can prove by induction that this is equal to 0 for all n belonging to the set of natural numbers. And this part I am just simply mentioning, I am leaving it out for you. You have to fill in the details, supply the details. This in turn implies, of course it just simply implies what we ultimately are required to show, that all the ans are 0. And here the solution ends, and by these exercises also end, and the video also ends. In the next part we are going to see rearrangements of series. That is, if we have an infinite series, what happens if we rearrange the terms in some manner? Would that affect convergence? In general it would affect convergence, but there is a particular class of series, these things which are absolutely convergent series, that surprisingly stay unaffected. Unaffected means if you rearrange the terms, the series itself will change, but the convergence will not change. The nature, if originally the series is convergent, it will still continue to be convergent, and the sum will also not change. I hope I am saying it correctly. Okay, I cannot exactly remember this thing about sums. I think the sum will remain the same if I am remembering it correctly. However, what is even more interesting is that if a series is conditionally convergent but not absolutely convergent, then for example this series, we know from the alternating series test that this series is convergent. But if you consider the absolute values of the terms, then you get the harmonic series, which also we have shown that it is not convergent. So that means this original series is a conditionally convergent series that is not absolutely convergent. That type of series shows us hell. I mean, when we are looking at its behavior, when we rearrange things, hell in the sense that there is a result due to Riemann which tells us that with this kind of series you can do absolutely everything. In what sense? You choose any real number, there exists a rearrangement of this series that will give you a series. After you perform the rearrangement, it will change and you will get another series that will converge to R, that can be arranged. What more is true is that there also exist rearrangements which will take the partial sums towards infinity and also the partial sums towards minus infinity. So you can do absolutely everything that one can do with a series if you have a conditionally convergent series that is not absolutely convergent. Whereas if you have absolute convergence, then with that also you can do anything, nothing will change. Not even the sum will change. I think I am saying it correctly. Okay, I am correctly recalling. Convergent series remain convergent with the same sum irrespective of how you rearrange the terms, and divergent series remain divergent. No, that is not true. What the hell? Divergent series won't remain divergent because they are not conditionally convergent now. That is, an absolutely convergent series will remain convergent. That's what I wanted to say. If you have a series which looks like this, okay, which is absolutely convergent, that means this series is convergent. Then you rearrange the terms. Technically what that means is that in place of n you just put phi of n, where phi is some permutation of the index set, that is the set of all integers which go like this. Then this series also is convergent and converges to the same sum. Okay, we will see these things in the next section. And the next video will be on this next Tuesday. So we have recently done what? Calculus. So this coming Tuesday, let us do number theory once again, and then we will do graph theory. So with that, I just end things for tonight. If you want to say something positive, negative, you can use the comment section below, or you can mail me at my address, which will be there in the description. So see you on Tuesday with number theory, where I think we are right now going through exercises on Euclidean algorithm. So that's it. So until this number theory video, this is me, Lucifer, from a mathematical room. Have a nice night.